and magnetic fields that fulfill those constraints. Well, then what I can prove is that the shape of the magnetic and electric field for later times, it's only given by the evolution equations. So we don't need to use the constraints again. So at time 0, we use the constraints, we get an electromagnetic field, and then later on in time, we only evolve it using the evolution equation. And this problem is well posed. I mean, you do get one solution. So at a further time, later time, you get one solution. So a unique solution. So let's see what happens in GR. What happens in GR is the following. So we have G00, that means the time component of Einstein equation, but doesn't have any time derivatives. So we believe that will be the constraints. Now we have the G0I, that means the time and special, and we have 3 equations for that component. They have first order time derivatives. Well, in contrast to Maxwell equations, that are just first equations of first order in time derivatives, Einstein equations are second order in time derivatives. Therefore, the equations that only have first derivatives will be also constrained equations. And finally, the special component of Einstein equations, the IJ components, where I and J, remember, are special indices, have second order derivatives in time. And the question is, can we do the same as in Maxwell theory? Can I give initial data, that means the shape of the metric and its first derivative, and for time equals 0, let's say, and then use these evolution equations to get the solution of the metric for later times? And the answer is yes, but it's not obvious why. So the first thing is that these equations are linear in second order derivatives. That means even though these equations are non-linear, at least for the evolution part, so the time dependence, the second order derivatives, the equations are linear. So that simplifies the question in a big deal. And the other thing one has to notice is that G mu, remember, is this metric. It is symmetric. By this discussion we had of measuring distances. And therefore, any symmetric matrix with 16, of 4 by 4 has 10 independent components. So these 10 independent components are the unknowns of Einstein equations. Here, remember the metric G mu have 10 components that are functions of the space and time. So these functions will give you here the derivatives of these functions of space and time, the Einstein equations, and you need to solve for those values. So the equivalent to the electromagnetic field are the components of the metric. So we can actually do the counting, and we have 6 evolution equations. Why? Because we only have the special part of the Einstein equations that give us the evolution equations, and that's also symmetric. And that means we have 10 unknowns, and we have 6 equations. So it looks like we've got a problem, because, for example, in Maxwell equations, we had enough equations. We have 2 equations, and we have 2 unknowns, the electric field and the magnetic field. So that was enough. Here, we have a problem because we have 10 unknowns and 6 equations to evolve them. So the key difference is that we're missing something. And what we're missing is the reference frame. So in GR, there's always this choice of coordinates. We can choose our reference frame so that we can kill 4 of those 10 components. Why 4? Well, we can choose a time, we can choose a new coordinate x, a new coordinate y, and a new coordinate z. That means we can choose them so that 10 of these unknown components are given. We can choose them to be whatever. So that means only 6 of them are independent in a given reference frame. And then I have enough equations to solve for these variables. And because the equations are linear in second derivatives of time, then by the properties of differential equations, I can prove that the solution is unique, as in Maxwell equations. So that means Einstein equations are well posed. They give you the right solution if you give initial data. There's only one unique solution. So that was on the left-hand side. Now let's discuss a bit what happens on the right-hand side of the equations. We have this energy momentum tensor. So a popular choice of this energy momentum tensor is what is called a perfect fluid. And it's popular because it's the simplest thing we can put. So imagine we got here, for example, you. Can I describe you as a fluid? Yes or no? That'll be the first question. So it depends. If I look from far, far, far away, so for example, imagine we're in a stadium, there's a football match, it's packed the stadium, or a cricket match, it's packed, and we want to see how people leave the stadium, we can definitely model that as a fluid. And it will be extremely accurate. And that's because the scales involved in the system are a lot bigger than the human scales of the interactions between humans. So from far away, you will actually see that they look like a fluid. So that's why it's, so in cosmology, this is special. Why? Because most of the things we see in cosmology, we can model them as fluids. But now the fact that it's perfect is just the fact that we're forgetting about all the exotic properties of fluids. So we're not taking viscosity, so we're not dealing with honey. We're not dealing with heat flows, so nothing that burns, for example. And something interesting is that we don't care about fluids that actually have a special direction. Right? Just for example, water. Water doesn't have a particular direction that is preferred over, a bucket. And that's what is called a perfect fluid. In mathematics, it's just a fluid that is described by its density and its pressure. That's it. And the energy momentum tensor takes the following form for a fluid. So here is the density, the pressure, times this unit velocity of the fluid, so how the fluid is moving with respect to the reference frame. And the nice thing, or the easiest way to remember what is the energy momentum tensor of a perfect fluid is actually to put one index up, one index down of this energy momentum tensor, and then remember that's just take this one and contract it with a metric, and what you get is minus rho in the 0, 0 component, and then plus this for the special components. Now remember we have the Yankee identity for the Riemann tensor. That implied, so sorry, this tensor here, the divergence of this tensor should be 0. I think it's here. So the divergence, the covariant divergence of this tensor is 0. So this is Bianchi identity. So now if we apply this divergence to the whole equation, you get 0 on the left-hand side. And then you should get that the divergence of the energy momentum tensor is 0. What does that mean? Well, it actually has a nice interpretation. It's nothing but energy and momentum conservation. So, any new theory that you develop, you must be sure that it actually goes back to the known theories that you had before in a given limit. So what is the theory of gravity that we had before GR? Newtonian gravity. So we should make sure that GR has a limit in which it actually reduces to Newton's law. So how do you do that? Well, you have to recall Poisson's equation for Newtonian gravity. So remember the Newtonian potential. You take the Laplacian of it, you get that it is sourced by the density of matter that you have. So now look, this is a second order differential operator over some quantity, some function. Not only that, remember the energy momentum tensor of the fluid, one of the components has the energy density. So it is that. So it will be natural to relate this right-hand side of Poisson equation to the energy momentum tensor when we put more indices in that equation. And since on this side we have second order differential equations, we might expect that the Einstein tensor gives you the Poisson equation. So this is not a proof. This is not I'm showing you. I'm just schematically showing you how Einstein equations can translate into Newtonian physics. So to do it formally, what you do is you take Minkowski's metric, so it's -1 plus 1 in dx, dy, and dz, and then take another function, which is in the dt component and the dx, dy, and dz, and it's this phi. So you just take this particular metric, put it into your Einstein equations here, and what you get is the following. What you get is that the 0,0 component of Einstein equation is nothing but 2 times the Laplacian of phi. And then, because the 0 component of the energy momentum tensor is this minus rho, what you get is Poisson equation. And then also, you get the geodesic equation. Remember, the geodesic equation had a second derivative of the position with respect to time times the Christoffel symbols. Remember? Those Christoffel symbols for this particular metric are nothing but first derivatives of the equation. And now you recognize this. This is the second law of Newtonian dynamics, and you get the Poisson equation. So Newton equations give you Poisson equation. Sorry, Einstein equations give you Poisson equation. It's one of the components. And then the geodesic equation gives you the second law. So we have recovered Newton from GR, but now is there a principle that actually it's more general where we can derive Einstein equations from? And I'm sure you've seen this principle. These are variational principles. And the way to do it is what is called the Hilbert-Einstein action. So remember, the right way to construct an integral is with this determinant of the metric and the measure. And to get Einstein equations, what you need to put is a scalar function that is given by the reach of the scale. And then you can put a piece that it gives you the metric. So if you take the variation of the metric, sorry, the action with respect to the metric, and you demand this to be minimal, to be an extremum of this action, what you recover is the Einstein equation. So the variation of this piece minus the determinant, well, the square root of the determinant of G times R gives you the Einstein tensor. And then when you take the derivative of this matter Lagrangian with respect to the metric, what you get is what is called the the energy momentum tensor. So you actually recover Einstein equations. But there is still a bit of freedom in this action. Why? Because we can always, without breaking anything, any of the assumptions of the theory, we can always put a constant here. This is what is called a cosmological constant. And what you get by doing the variation is you get these more general Einstein equations, where a part of having the Einstein tensor, you get a constant times the metric. So this is an important constant, since it seems that our universe is expanding in an accelerated way, and it all points to a cosmological constant. So initially, Einstein put it there because he actually wanted a universe that was static. That means it was not evolving, it was not moving. So he put that constant to stop the expansion of the universe. And what he realized is that that was not very steady. It was not a good idea. And then we actually found observationally that the universe was expanding. So he actually described that as his biggest blunder, his biggest mistake. But now it seems that the cosmological constant is coming back, and it's a point of research at the moment. And I'll show you later why. So, there's an alternative way of deriving Einstein equations from this Hilbert-Einstein action. And GR is so perfect that the two alternative ways of deriving the equations give you the same result. That doesn't happen usually when you go beyond GR. So this is a formalism called Palatini. And basically the idea is to say, okay, so remember I had these Christoffel symbols, which were the connection in terms of the metric. So what I can do now is to think that the connection is not related to the metric, and I can take it as an independent object. So I can minimize the action, I extremize the action with respect to the connection and with respect to the metric. So that means this Ricci scalar is written in terms of the G and the gammas, but I'm not relating the gammas to the G's. So, as before, the variation with respect to the metric gives you something that looks like Einstein equations, but G mu nu is now written in terms of gamma and G, not only G. However, when you actually write the equation of motion derived by extremizing with respect to the connection, what you get is that the covariant derivative of the metric is equal to 0. And remember, from here, you can derive the Christoffel symbols, and then you can put them on to get Einstein equations. Okay?
And then you are assuming that the matter Lagrangian doesn't depend on the connection, right?
Yes, that is true.
What if it does?
Then you don't get GI. You get something that is not GI. So this is Hilbert-Einstein. This matter Lagrangian is actually, it only has the metric. And it's what is called minimally coupled. When you go beyond that, you open Pandora's box and you can get whatever you want. So we'll talk about that tomorrow. So you do recover Einstein equations. So, as you were taught in your classical mechanics courses, you have this action and Lagrangian formalism, but you also have this alternative formalism based on Hamilton's proposal. So let's see how that looks in GI. So this is also called the ADM, or 3+1 decomposition of formalism. So let's see. So remember, the metric is just a matrix that has a bunch of components, bunch of functions, right? 10 independent functions. So I can put different names to the components, and still there will be functions. So I can call the 0, 0 component just by this function n plus this bit. On the, do we have markers? Okay. So what I'm doing is I got the metric and I'm splitting it into 0, 0 component, 0 I components, and then the ij component. So this first part is just that n squared function times this part. these components here that look like vectors, they look like normal vectors, three-dimensional vectors. They are given by this n, the index k, and then the metric here remains the same. So schematically, what I'm doing is splitting time and space. So n is called the lapse function, and it just tells you the following. So imagine I have, at a given time, how the curved space looks like. And at a later time, I might have that the space gets modified. It has a different curvature. So the lapse just tells you how to move in time from one sheet to the next one. So schematically, this is just like taking what's it called? Bread, the bread that comes in boxes and is sliced like bimbo. Sorry? Bimbo's bread, yeah, bread. So imagine you take a bimbo, that's your space-time. And the fact that I'm foliating, I'm cutting the space-time in slices, that is this decomposition. So I'm splitting a space, it's just one slice, and the way you go from one slice to the other one is just given you by this lapse function in terms of time. However, I can have that a point in one slice. So for example, you know, when you leave the bimbo there for a few days without eating it, you start getting mushrooms there, yeah? It starts going bad. So what is true is that, you know, the mushroom doesn't propagate straight up from one slice to the other one. You can propagate slightly shifted to the next slice. Well, that is being measured by this shift function, this Ni or Nk. Okay? And then finally, I have this special matrix. This special metric, gamma, and that's just telling you what is the curvature of your bimbo slice, right? So it's like, I mean, imagine you squeeze it, and then your slices are not straight. So I think we have enough with the lines. Let's lose it, por favor. So something I can do is to take derivatives with respect to the time of this metric. And what it's telling you is the extrinsic curvature. It means it's telling you how much your slice is curved, but outside the slice. So this tensor called Kij, that's called the extrinsic curvature. And what it happens, it turns out that I can actually write down the Hilbert-Einstein action, this R, in terms of this K and H, and I get the following expression. So this action is just something that looks like, you know, a variable dot times its canonical momentum minus n times a function and minus ni times another function. And the function h, the Hamiltonian, is just given by the special Ricci tensor. So remember, we had a matrix that was the spatial part of my full metric. From there, I can actually build the three-dimensional Riemann tensor, and from there, the Ricci tensor, and from there, the Ricci scalar. So that is that Ricci scalar for the three-dimensional piece. And it also has this extrinsic curvature piece. So look, if the extrinsic curvature looks something like a momentum, then I get something that looks like momentum squared. So this is something that looks like kinetic term, and this is the potential term. So this is why it's actually a Hamiltonian formula. So now the interesting feature of this Hamiltonian formula is in DGR is the following. So now look, the only dynamical variables found in my action are the following. The only ones that have time derivatives are the gammas. I don't have time derivatives for n or ni. So look, the case, do not have time derivatives of ni or n. And there is an n here, and there is a gradient of n, but there are no time derivatives now. So that means there are no time derivatives here. That means the only propagating degree of freedom, the only real degree of freedom, are the gammas. So only the gammas are dynamical. So in this way of writing GR, only the special metric is dynamic. So the time components do not play a dynamical role. However, they are linear at the level of their Lagrangian. That means if you do their equation of motion, they're like Lagrange multipliers, and you get constraints. You get that h has to be 0, and hi, which has this momentum constraint, also has to be 0. So we're led with a theory, right, that the Hamiltonian has to vanish, has to be 0. So in all of your examples of classical mechanics, you had that the Hamiltonian was the energy, and you would set the energy, if it was not changing in time, it will be a constant, and from there you will construct your solutions to the system. In GR, that's not true. Energy, it's difficult to define, but the Hamiltonian is always 0. So now let's count the degrees of freedom. So remember, we started from these 10 components of the metric, and we said that by choosing a reference frame, we could kill 4 of those. That meant we had 6 independent components in the metric on a given reference frame. But now we have these 2 constraints. So this is one constraint, this one has an index, so actually there are 3 of them. So if you add them, there are 4. So 3 plus 1 constraints. These are relations between my dynamical degrees of freedom. That's what a constraint is. Right? It doesn't have time derivatives. It only has relations between them. So that means out of these 6 constraints, I have to remove 4. Sorry, these 6 independent variables, I have to remove 4, and I end up with 2. These are actually the 2 modes that have that compose a graviton. A graviton is the particle that carries the gravitational field. So, let's look at these gravitons in more detail. So something we can do, as we did for the Newtonian metric, remember the Newtonian limit was expanding the metric around flat space by this extra function that we call phi. Right? So now we can do something similar, but with a more general function, actually, a more general expansion around flat space. So we have the metric, we take the flat metric, Minkowski, and we add a perturbation. That means a very small quantity, but in all components of the metric. Not only in the diagonal piece that we did for the Newtonian limit. So, well, by demanding here, so constructing some new variables instead of h, this h bar has this combination, and its divergence is 0, so something like the Einstein tensor. What you can prove is that to linear order in epsilon, so you just take terms that have epsilon equal to 1, epsilon to the power 1, what you get is that Einstein equations have the following form. So you just get a box operator, and if you don't remember what box is, it's just the second derivative of time plus lambda squared. This is what box is. So that is exactly a wave equation. So what I get is a wave operator acting on H, and it's sourced by matter. So if we go to vacuum, that means no matter, no energy momentum tensor, what I get is just the wave equation. So this is a wave propagating in Minkowski space-time. So we'll talk about these waves in more detail. So let's think of a plane wave. That means a wave that is traveling in the z direction. I can always write it just by having a component in the z direction, and times a unitary, a constant matrix. So remember, we had a definition of this h bar that was given in terms of that, so that its divergence was 0. So let's see how this divergence looks when I take this decomposition. So this h hat is a constant. So this is just a wave operator. So remember k dot x is just the first component of k that we can call omega times t with a 40 minus 1 plus, let's say we're moving in the z direction, we have a kz times z. So this is a wave traveling in the z direction. So if you do that, this restriction just tells you that this k vector times h mu nu is 0. That means it's orthogonal to the way we're moving. And then we also have this operator. This operator, the wave equation, just tells you that it has to be a null vector. So how does it look? The two conditions, orthogonality and null. It just tells you that this matrix h hat has to have the following form. So, especially time and the z component, and only in x and y it has different constants. So it has one constant in the diagonal and another constant in the off-diagonal terms. This h hat. This will be h hat. And these are precisely the two modes that we talk about, the 2 degrees of freedom of the graviton that we counted before. So when it comes to this wave equation, so this is a wave propagating in the flat space-time, we actually have two possible polarizations. So this H plus, it represents, how space-time is doing this in the x and y direction. So let's imagine that's a set, and here we have x and y. So the wave is moving that direction, and is changing space and time. Remember, we're talking about a perturbation around flat space. And what is the perturbation doing? The perturbation is h. So first, it's growing in x, then growing in y. So shrinking in y. That's why it has a minus sign. So the x component, for example, is growing, and then there is a minus. So that means it's shrinking in y. And that's why we get this ellipse. Then it goes back to the position, and then we get the opposite. Why the opposite? Because remember, here we have trigonometric functions. So we have cosines and sines. So you get the two signs. And the off-diagonal terms, they do the same, but in a 45-degree axis. So, physically, what does it mean? Well, what it means is that, so if we have flat space-time with nothing there, GR predicts that there could be waves traveling through that. And if we go back to this picture we had of the GR being a sheet, a bed sheet being pulled, what you get is that a gravity wave, a wave on this space-time, is nothing but a ripple on the sheet. So imagine you're holding the sheet, right? And I do like that. You get a traveling wave. Okay? So that's what gravitational waves are just ripples of this sheet. And they have two polarization modes. They have this plus and this cross mode. And it's exactly the same as the photon. The photon has two polarization modes. And there's something deep there related to the spin of the photon and related to the spin of the gravity. We'll not get into the detail. If one of you already knows about spin, can come and ask me. But at this point, just think that these are modifications of space-time that are oscillating, not the wave. So, now we measure them. Well, the first indirect measurement of gravitational waves. So the big problem with gravitational waves is that compared to electromagnetic waves is the amplitude. So let's go back to this. So in electromagnetism, you get a dipole. You need a dipole to produce a wave, an electromagnetic wave. And you know that's the way antennas work. You get an antenna, and you get a charge moving on the antenna. That produces an electromagnetic wave that propagates in space and time. Well, in GR, the problem is that the source actually has to have a different charge distribution. It cannot be a dipole, but it has to be a quadrupole. So it's something like looks like that. These are quadrupoles. So it has to be a distribution of mass. So now remember, the charge in gravity is the mass. So we need to have some configuration of mass that looks like this. And it has to change in time. So when we do that, we can produce a gravity wave. The problem is that then the gravity wave, the amplitude is very small if we compare it with electromagnetic wave. And that's why it took us 100 years to actually see it. So the first indirect evidence of them was based on something called the pulsars. So pulsars are neutron stars that they emit a jet of light in one direction. So they're like lighthouses in the coast. You know, a lighthouse goes like that, and gives you a flash of light every certain time. So these pulsars, that's what they do, and we can measure their position very accurately. Why? Because we get these pulses. And these pulses are so regular that we actually can compare them with the best clocks that we have here on Earth. We have a precision of 10 to the minus 14 seconds, and they are comparable to atomic clocks, which also have the same position. So that means the new definition of the second is based on either atomic clocks or pulses. So with that precision, we can actually tell the distance, well, the position of a pulsar. And then we can have two pulsars orbiting each other. And what will happen is that the periods will change. Why? Because this, having two pulsars, it's a quadrupole configuration. The quadrupole configuration is emitting gravitational waves. So the system is losing energy. Because it's losing energy, they get together. They get closer. If they go closer, they have to speed up. So you get a change in the rotational frequency or the orbiting frequency of the binary pulsars because of gravitational wave emission. And Holtz and Taylor from the 70s started putting dots on a chart according to the period shift. So how much it was, they were getting closer. And those are the experimental dots. And the line that goes through them is the prediction of general relativity. So this is not direct evidence of gravitational waves. It's just saying, look, if we've got a system that is losing gravitational waves in the same way that general relativity does, then we get a match. Okay? With observations. But by no means we have seen it at this level. They won the Nobel Prize in 1993, but there is a more recent story about these gravitational waves that I'm sure you're all aware of. And this is discovered by I-2. So basically what we need to do is to measure deformations of space and time. So remember we have this mode, for example the x, that is growing the y direction while the x is shrinking. Yeah? And the big question is how much is, for example here, imagine there's a gravitational wave like coming through this direction. Well actually the root will shrink in this direction and expand in that direction, and then the opposite at the next time. So can we actually measure that difference? Well, the problem, as I told you, is that the amplitudes of these waves is very small. We'll see in a second how small. So, but then how can we measure distances so precisely. So one idea was with solid pieces of something. Those were the early detectors, but they didn't have enough resolution. So now we use interferometers, and basically the idea is to say, okay, I send light from here to there and bounce it, and then from here to there and bounce it. If I have control over the distance, I know that the pattern of interference will be given. However, if these distances get modified by a gravitational wave, then the pattern will change. And the big question is if I have the resolution to actually see them. So, just a few of these interferometers. So we have really small ones that nobody talked about. I don't know what happened to them, but there was one in Birmingham a few years ago. There were small ones, but really the big ones are the interesting ones because we can see astrophysical production of gravitational waves or cosmological. So LIGO, in particular, is made out of mostly two detectors. Well, there's a third one with Virgo in Germany, and there will be NEO in India or Japan. But basically, the two ones that detected last year gravitational wave are in the US, and one is here, the other one is there. And these are these interferometers that have 4 kilometers arms. So we're bouncing the light 4 kilometers that direction, coming back, and in that direction also 4 kilometers back, and then we're measuring the interference pattern. Another proposal that is being worked out and will happen maybe in 10 years is something called LISA. This is an interferometer in space. And basically, the idea is instead of putting an interferometer like this in space, we're putting a triangle, so we're actually measuring 3 distances. And these are just satellites based on one of these Lagrangian points of stability, instability of the Earth, Sun, Earth system. Sun, and the final proposal is taking these pulsars, which are extremely good at measuring time, and using them as an interferometer. So taking 50 of them, and then just checking if there were deviations that actually would correspond to a gravitational wave passing through them and us. So this is what is called the pulsar timing array, and it's still in development. I don't know when it will be available. So let's see the kind of resolutions that they can get. So this is something called the strain. The strain, that means how much of a given distance they can tell it got modified. So of these, for example, 4 kilometers, what is the resolution of these detectors? How much they can tell you of a change on those 4 kilometers. And advanced LIGO, for example, which is here, advanced LIGO, yeah, one of these lines here, you can go to 10 to the minus 24. That means if you get a 1 kilometer distance, it can tell you what is a change kilometer of this magnitude. All these zeros and a 1. That means LIGO can tell you a change on its arm of the size of 1,000 of the size of the proton. Imagine taking a proton, now dividing 1,000 times the proton. Well, that is the distance that these detectors can measure in 4 kilometers. Okay, so the most precise detectors they are there for distances. And just almost 2 years ago, 14th of September 2015, they saw this signal. So actually the noise is way below the signal. So most of the signals that they have seen after this are actually within the noise. They actually have to do a lot of data analysis. That's what Max will be next week. But for this particular event, they didn't have to do any of that. It was so obvious, even by eye, you could see it. And this is the detector in Hanford, so in this coast, the west coast, and then one in Livingston detected this one. So if you put one on top of the other one, you get but they are very similar. So you can clean the signals like this, and this is the noise version. So this is an event that it's real. I mean, if you think it was just a fluctuation of the machine, it's a fluctuation that will happen in more than, you know, something like 200,000 years. So almost 1 billion years. And this apparatus was only in operation for like a day when it happened. So this was not really a fluctuation. I mean, this is a signal that in terms of statistics has more than 5 people. And what they actually found is that by analyzing the signal, they can tell you what were the two objects that collided. So we have very massive black holes orbiting each other. These are black holes of almost 30 solar masses, and they went around. They lose energy because of gravitational radiation, just like we had for the binary pulsars. They merge, and then they get this peak. That's exactly when they come together, and they become a single final black hole. And well, the interesting thing is that, as people from LIGO put it, is that for the first time we actually heard the universe. So before that, most of the information we're getting from the universe is just by light, seeing, but this was the first time that we actually heard it. And that's because the frequencies that we're talking about, these frequencies, are actually the same frequencies that we hear. So in principle, you can translate this signal to sound, and you can actually hear it. So it opens a new area of astronomy based on gravitational waves. And the interesting thing is that we can prove more about the theory of gravity behind it, so we can see if it's GR. So I think I will stop here today. If you got any questions, we have a few minutes, so please ask. First question.
Is it possible to like when we use telescopes that use radio waves or that infrared waves? Is it possible to engineer a telescope that would detect gravitational waves?
So the first thing is that all these electromagnetic waves we're talking about, for me that's the same as signal. So we have a lot of experiments that run in different wavelengths of the electromagnetic spectrum. And a lot of them, for example, X-ray, microwaves, radio, they're all the same thing. I mean, it's just electromagnetic field oscillating, and then you measure it. So for me, that's the same as the visible one. So that's why I call it signal. This one is a different one. This is really measuring our detector is spaced. So we're actually getting space. It's getting modified by a wave that is passing. So it's not really a photon that is traveling. It's not light. It's really the space that is getting modified. And there you have different frequencies. The thing is that the frequency depends on the object you're observing.